We're now going to derive a very important equation in fluid mechanics, and that equation is the Bernoulli equation. So what the Bernoulli equation will provide is it will provide a useful relationship between pressure, velocity, and elevation. So we'll get an equation that will have pressure, we'll have velocity in it, and we will have elevation z. And this will be, we'll come up with a function for it, but it will then be written in terms of a constant. So we'll have some function of all three of these variables is equal to a constant. So that's what we're going to get out of the Bernoulli equation. And the place where we're going to begin with this derivation is we're going to begin with a control volume analysis using the linear momentum equation for a little piece of fluid between two streamlines. So let's begin with that. So what we have here is we have a little differential control volume, and it's indicated in red. And so this is a little differential chunk of fluid, and it is bounded by a couple of streamlines. So there's one on the top and one on the bottom. And what we're examining, we're examining the change in the fluid as it's going from this point here to this point here. So the inlet to the exit. And we'll notice that as the fluid goes between the inlet and the exit, pressure goes from P to P plus dP, and the velocity goes from Vs to Vs plus ds, and the area can change as well. So we can either have the streamlines opening up, getting wider, or getting narrower and converging. And what we're assuming as well, and this will be one of the assumptions here, is that the density is not changing. So we're dealing with an incompressible flow. So let me write out the assumptions for what we're looking at. Okay, so we're dealing with a steady flow, frictionless flow, no shear forces, and incompressible. So the density is not changing. So what we're going to do, we want to apply control volume analysis, and we're going to use two different techniques. One, we're going to use a continuity equation, mass conservation, and the other one that we're going to use is F equals ma, or the linear momentum equation. So let's go about applying those two equations to this system. So that is the continuity equation. Now to begin with, one of the assumptions we made was that we're dealing with steady flow. So right off the bat, this term disappears. And then what we're left with is the mass flux across the two control surfaces. If we look back at our schematic, where is mass crossing the boundaries? Well, it's bounded by streamlines. We have a streamline up here and we have a streamline here. So the only place the mass is crossing the boundary is going to be on the inlet, and we have the inlet there, and then on the exit. So those are the two control surfaces where we have mass crossing the boundary, and those are the two that we will work with. So for mass crossing on the inlet boundary, if you recall what we have, remember the area vector is always pointed in the outward direction, and here we have a velocity vector. Well, it's v in the s direction. I'll draw it that way. So that's going to give us a negative term for the first part of the mass conservation. And then on the exit side, there we have a situation where we would have, again, dA. Actually, that should be A, not dA. I wrote A plus dA. But that would be the area vector, A plus dA. And then we will have Vs, and then we had Vs plus ds. But we know that the velocity and the area are pointing in the same direction, and consequently, this here will be a plus. So the velocity was Vs plus dVs, and then the area was A plus dA. So that's what we get from continuity. We can then simplify and rearrange, and we get So we get this relationship here, and what we're going to do, we're just going to park that, and we will come back and use that in a few minutes as we look at the momentum equation. So let's now move on to looking at applying the momentum equation. And what we're going to do, we're going to apply the momentum equation in the direction of a streamline. So that means we're applying momentum in the direction of S. So that's what we get for the momentum equation. Now what we have on the left-hand side, we have the surface forces and we have body forces. So surface forces, there is no viscous shear, but there is pressure. And then we have FB, that's the body force. And then on the right-hand side, we have the time rate of change term, so that's going to disappear. And then we have the mass flux crossing the control boundary and exchange of momentum. So let's begin with the first term here on the left-hand side. We'll begin with the pressure force. So let's take a look at that. Okay, so let's do some explaining here. First of all, the first term here, this is the left-hand face of our little chunk of fluid. So remember we had a control volume that kind of looked like this. So that is the left hand, and then this here is going to be the right hand face, which is the second term. And then we have this third term. What is that representing? Well, what that represents, we're going to take the pressure, average pressure in the middle, which we'll say is P plus dP over 2. And let's assume that the streamlines are getting wider. Well, we need to apply the force due to that expansion in the streamlines. And that's what this term is doing. And so the amount that the streamlines may be increasing could be dA. And so it's just the pressure at the midpoint multiplied by that change in area term. And so if the streamlines are converging, that would then be negative, and you'd have a force in the left-hand direction, in the negative S. But here we're assuming that they're getting wider, and so you would have a force in the positive S direction. So that's what that is referring to. So there we have an expression for the surface forces. Let's now move on and take a look at the body forces. Before we do that, let me just rewrite this a little bit to clean it up. Okay, so what I've done here is I've just expanded out some of the terms, and if you go through the math, you'll find that some of them do cancel out. It's not the cleanest, but that's where we will stop with that part. And next what we will do is we will move on to take a look at the body force. So what we have here is the component of gravity acting in the direction of the streamline. And through trigonometry, what we can do, if we draw our gravity, we said the gravity vector was acting in that direction. If we want to evaluate the component of gravity along the streamline, what we need to do is use trigonometry here. So I'm going to set up a right angle triangle right here. And GS, that would then be equal to minus sine theta multiplied by G, the gravitational constant, where in this diagram, this angle here is theta. And that's basically the angle that our streamline is making. And so with that, we can rewrite the body force in the following manner. And this here is a representation for the volume. And what we do, we have our little chunk of fluid, and remember we're assuming that maybe it's getting larger, so we have A here, A plus dA divided by 2, and then the length of this differential element is ds. So what I'm doing is I'm taking the average area at the middle and assuming that that's a cylinder, and then getting the volume. So that gives us one part of the body force, but there's another trig relationship that we can use, and that enables us to do a little bit of a simplification